Hello. So this time we are going to explore the question of what is a function? Well, uh, a function is a relation uh, between uh, two collections uh, that we call the domain and the codomain, respectively. Uh, well, uh, but not only this, it's not only a relation, we also have to impose certain conditions where each member of the domain is related to only one member of the codomain. And well, what is this saying in terms of what the function is, right? Well, it's telling us that the function is total on its domain, so every single element of the domain is associated with something on the codomain, and is deterministic as there's only one of them. You can immediately detect or think of the function as an input-output relation to some extent, right? So where is that we see these things? Well, let me provide a couple of examples. Right? One that is, for example, given by division. So I'm going to say the following. Every integer um, has a remainder modulo 3. What is this? Well, when you take an integer number and you divide it by 3, well, it provides a remainder. That division results in a remainder. The question is the following. Where is that the function is arising from just stating this, right? And we're indicating here. Well, let me exemplify. Let me put it in all its details, right? The first thing is I'm going to state the domain, right? The collection of integers. Secondly, I'm going to state the codomain. The collection of remainders modulo 3. Well, in this case, well, this relation that we're stating here is a function because, well, every integer leaves a unique remainder when divided by 3. So, what can we say in this regard? For example, if we divide 5 by 3, the remainder is 2. Here's another example. One a little bit that it's kind of the things that we have been seeing more often, right? Every real number has a square. I'm not saying square root, square. For example, the square of 3 is 9. Okay? Now, in this case, we have to induce a function here. But, as I'm going to say it in a second, right? what I'm saying, what we're stating here, well, produces a function. What function could this be? Well, first thing, as usual, we have to state the domain. And what would be that domain? The collection of real numbers. What would be the codomain? Well, it's going to be a repetition, the collection of real numbers. Why is this? Well, think of this. I'm talking about real numbers, and when we square them, well, the expectation is that we get a real number. So we see that each real number is associated to its unique square. For example, 3 goes with 9, and negative 2 goes with 4. Now, one of the things that we can say here is that in this last example, we may also graph this function. How so? Well, on a piece of paper, right? Because we associate to the real numbers a line, right? So we'll start like this. Well, here is my line. Then I fix a point on that line to indicate that this is the origin. Then to this line, I also attach on a plane right here a secondary line that is perpendicular to it. I choose directions, perpendicularities here. I also choose a unit of measure, right? Indicating this goes a positive, this is a unit of 1. The same goes here, right, on the secondary line. And now we're able to graph it, because in this case, well, for example, we have 1 here. We associate with this a point here, which would be the point 1, comma 1, right? The square of 1 is 1. Here, the square of 0 is 0. So now we have a point. The square of negative 1, which would be in the opposite direction, well, is 1. The square of 2 is 4. So we're showing something here. The square of negative 2 would be negative 4. Of course, we would like to actually draw it. So I'll try to come up with a nice graphical representation of this function, right? We think of this as extending in both directions, y equal to x squared, the curve on the plane given by that equation. So, but then this says, look, this is not a very common way of seeing functions. Instead, we'll introduce the following notation, which I think would be fairly useful for us. We can say, look, whenever we have a function, we will give it a name. Since this is just being generic, we would say a function going from D to C, where in this case, well, here D is the domain and C is the codomain. Now, we would also write y equals to f of x to indicate, which is the shorthand to say y is the only thing in the codomain associated to x via f. So, if we were to give our names, right, to the function that we're representing here, for example, we can say, well, look, the collection of integers, well, that one has a special symbol, which is a z. The collection of remainders modulo 3, well, there's no special symbol, but we can shorthand it in this way as using brackets, curly brackets, 0, 1, 2. And then we would have something like this. We would say remainder, I'm going to give it a name R, to say it's a function from the set, from the collection of integers to the collection of remainders modulo 3, 0, 1, 2. And for example, as we said before, that 5, when you divide 5 by 3, the remainder is 2, you can indicate that by a single equation. You would say, in this case, R of 5 is 2, because we're dividing by 3 in this case. Right? So, in this one, the one that is the second example, we would say, well, look, I can say that since the domain is a collection of real numbers, that also has a special symbol, which is a boldface R. So the codomain is also the same thing. So we would say the function that I'm going to call S, shorthand for square, would be a function from the set of real numbers to the set of real numbers, where the following takes place. S of x is equal to x squared. So instead of saying this, for instance, we can say that S of 3 is 9, and we can say that S of negative 2 is 4. So, not everything results, not all such relations results in functions. Let me provide the following example, which would be enough. Well, let me say it. So I'm gonna relate two quantities, two things, two collections. So relate two real numbers by declaring that they are related if the sum of their squares equals 1. Okay. So what happens here? In this declaration, we have two collections. I'm not going to say domain and codomain because I'm not sure whether this is actually a function. Actually, this won't be a function. So what would be the first collection? Well, once again, we're relating real numbers. So the collection involved, the first collection involved here is nothing else but the collection of real numbers. What about the second collection? Well, same thing, real numbers. We are relating two real numbers. That would be the second one that is associated with this. Okay, so the question is this relation a function from collection 1 to collection 2? Well, the answer is no. That's the idea, right? The whole point of this example. And we can apply any of the following two arguments. What will be the first? Well, 3, the number 3, which is a member of the collection, the first collection, as it is a real number, is not related to anything in collection 2. Well, you may wonder, why is this? Well, let's explain. If they were, otherwise, there would be a y in collection 2, meaning a real number, such that 3 squared plus y squared equals 1. But 1 would be equal to 3 squared plus y squared, which in turn would be, well, greater or equal than 3 squared, because we're just squaring real numbers, and when you square a real number, it becomes 0 or positive. So I'm just getting away of that possibility, right, by removing that y squared. But this is 9, which is certainly greater than 1. So that cannot happen, right? The assumption that we made that this number will be related to something in this collection leads to a contradiction. So there is nothing like that. Or, right, we can indicate also the following. We can say 0, which is in collection 1, is related to two things. In collection 2. Namely, 0 is related to 1, and 0 is related to negative 1. Clearly, 1 is different from negative 1. Now, one of the advantages of this relation is that we can also graph it on a piece of paper. Because what is the thing that we're representing here? The sum of the squares is equals 1. Well, that's nothing else but the unit circle center at the origin. So, if we were to graph it, more or less, it would look like this. If we were to draw a vertical line, right? This being the x and the y, this being the units. Well, at x equals 3, right, you drop a line and you'll see that it doesn't touch the circle. But if you drop a line at x equal to 0 here right at the origin, you see that it touches these 2 points. And, well, look, there are 2 ways in which you can negate this portion, right, on the definition of a function. Each member of the domain is related to only one member of the codomain, only one, Look, here we demonstrated a member of the supposed codomain, I'm sorry, that is related to none. And here we indicated another member which is related to two or more things, right? So with this, let me finish and see you next time.